Today we're going to discuss Grover's quantum search algorithm. But before we go into its details, we need to discuss quantum gates. In our previous lectures, when we discussed quantum implementations of classical computations, we used quantum analogs of gates AND, OR, NOT, and these were permutation gates. So this means that they would take a standard basis of n-qubit space and just permute standard basis vectors. Obviously, we need more quantum gates. And so if we look at 1 qubit space, so which is C2, right? So what are natural transformations on this space? Well, one natural example is rotations. So ignoring that this is a complex space, we can just treat it as a real space and then take rotations of a plane, right? And so here we have R alpha transformation. So this is so cos alpha, sine alpha, minus sine alpha, cos alpha, right? So this is a well-known expression for the rotation matrix. And so then in our standard notations of quantum computing, so this says that R alpha applied to 0 is equal to, well, we take the first column. So it's cos alpha times 0 plus sine alpha times 1. And R alpha applied to the second basis vector. So it's minus sine alpha times 0 plus cos alpha times 1. So this is an orthogonal transformation of R2, and any orthogonal transformation of R2 extends to a unitary transformation of C2. And so this is a natural class of 1 qubit transformations that are not permutations, right? So obviously, and so they depend on a continuous parameter. And so today we will need one specific example of rotation. So we take the Hadamard transformation. So which is denoted by H. And it is a rotation in angle pi by 4. So the matrix of this transformation is 1 over square root of 2, 1 over square root of 2, minus 1 over square root of 2, and 1 over square root of 2. And it acts on the space of 1 qubit. An interesting thing happens when we take an n qubit space. And we apply the tensor power of Hadamard transform to the 0 vector, right? So here, well, 0 here we understand as n-bit string of zeros, right? So let's take this. So what does it mean? So this n-bit string of 0 is a tensor product of single zeros. And the tensor power of Hadamard's transform is understood as operator that is where Hadamard's transform is applied to each component. So this means that this is H applied to 0, tensor product with H applied to 0, tensor product, and so on. So in each component we do the Hadamard's transform. So what's the result of this calculation? So we get so H tensor nth power applied to this 0, right? So this is kind of multiple 0. So this becomes, so essentially we use these formulas, right? So but here we have 1 over square root of 2. So what we get is 1 over square root of 2, 0, plus 1 over square root of 2, 1, tensor with the same thing n times. Now, what will happen when we expand this? So if we expand this product, then, well, we can pull out this 1 over square root of 2 from each factor, right? So we get here 1 over square root of 2 to the power n, right? And then in each summand, we have 0 plus 1. So when we expand this, what we see is any n-bit string may appear in this expansion. And each n-bit string will appear with coefficient 1 in this expansion. So what we can write is, so here we have the sum. Now, so n-bit strings will go, if we take the whole string of 0, so this is corresponds to k equals 0, right? So we write it like this. And the highest value of n-bit string is all ones. And all ones is 2 to the n minus 1. So what we get is we obtain this expression. So we get 1 over square root of 2 to the power n. And then summation k goes from 0 to 2 to the n minus 1. And this integer k is understood as its binary expansion as an n-bit integer. And so this is a very useful expression because this gives us a superposition of all possible inputs, n-bit string inputs. And so this state is very convenient to start our parallel classical computations, right? So if we need to run parallel classical computations with all inputs simultaneously, so this is an excellent starting point. So we take this state, and so then we can apply any classical, quantum implementation of a classical computation scheme, and we will obtain a superposition of all possible values. And so this is achieved by applying nth tensor power of Hadamard to just a basis vector that consists of all zeros. So basically, we're applying Hadamard's transform to each component. And so here, so we should point out that this state is actually not entangled, right? So because this is still factors as a tensor product of n states. Now, let us state the problem which we're going to solve using Grover's quantum search algorithm. So here we have the following problem. Suppose we are given a classical computable function f from n-bit strings to 0, 1 such that equation f of x is equal to 0 has a unique unknown solution x is equal to a. So we want to find a. Right? So this function assumes only two values, 0 and 1. And for most inputs, it produces value 1. And there is a single value for which it produces the output is 0. And this value is unknown. And we want to solve essentially this equation. F of x is equal to 0. So where there are many functions of this type which are sort of trapdoor functions. So this means that it's easy to compute such a function, but it's difficult to find solutions to such an equation. Similar type of functions are used in hashing. So the only difference is that for hash functions, so here we have not b to the 1, but b to some power k. And typically, so hash functions are used in checking integrity of documents. So we have a long document, so this n may be long, and we compute its hash, and we get a short binary string that reflects all bits of this long document. And so, for example, if we want to make this document secure, so we want to put a digital signature on this document, then it's easier, instead of putting a digital signature on the whole document, it's easier to put a digital signature on the hash. But because this function is sort of a trapdoor function, so given the hash value, it's very difficult to find a document that will have a prescribed hash value. Of course, so here we should have b to the power k with reasonably high k. But here we have a simpler situation, right? So we take a binary string of length n and convert it into a single bit. Now let's give an example of an interesting function of this type. Well, suppose n is 2 times m, and so we let some integer k be a product of two n-bit primes, p and q, right? So the fact that, m-bit primes. So this means that, well, p and q are prime numbers, and p and q are less than 2 to the power m, right? So this tells us that k, which is the product of p times q, is less than 2 to the power 2m, which is 2 to the power n. And let us consider the following function. So f of xy is equal to 0 if x times y is equal to k and x is less than y, and it is 1 otherwise. So this is an easily computed function, right? So we take two integers, we multiply them, that's easy, and compare the result with k. If the result is k and x is less than y, then the output is 0. If x times y is not equal to k, so then we get 1. And so here, if we restrict x and y to be m-bit integers, then here we are going to get a single solution, right? So, so this value 0 will be assumed only when x is equal to p and y is equal to q, assuming that p is less than q. So now, if we assume x and y to be two m-bit integers, then two m-bit inputs can be considered as a single n-bit input. So what we get is we get precisely a function f from b to the power n to b, right? So the input is n-bit strings, the output is either 0 or 1, and here there is a single input, right? And so the input here is a pair xy, for which f of x is equal to 0, because if we are told that k is a product of two primes, then there is a unique factorization of this type. And this factorization is difficult to find. So from cryptography, we know that factorizations of integers is a hard problem, and it's actually a basis of RSA cryptosystem. Now, let us go back to the general setting. For most computable functions of this kind, there is no clear algorithm how to solve such an equation in an efficient way. And so let's assume that such an algorithm is not known. So then the only way how can we solve this problem is by brute force. So this means that we're going to take all possible inputs one by one, and we compute the values. So we compute f of 0, f of 1, f of 2, and so on. And we just do this until we hit x equals a. And then we find the solution. So on average, so how many attempts do we need to do in order to solve such equation? So on average, so here we need the n over 2 attempts of brute forcing. So here n is 2 to the power n, right? So this is the number of all possible binary strings of length n. Now, with Grover's quantum algorithm, we are going to see that with a quantum computer, the same problem can be solved with square root of n steps, right? So in quantum setting. And so what we see is, well, this is a significant improvement. So square root of n is way, way better than n over 2. And additionally, this demonstrates quantum supremacy. So this clearly, there is no classical general method for solving this problem with complexity which is better than n over 2, because classically, brute force is the only thing that is available to us. Now, if we look at this integer factorization problem, right? So then classical complexity of this problem is square root of n, because all we have to find is we need to find a single factor, and a single factor p is between 1 and 2 to the power m, right? So which is square root of n here. And so then we only need to brute force, we need to take integers from 1 to square root of n, and then we try to divide k by this integer and hope that result is an integer, right? So because of this, brute forcing only requires square root of n steps. So if we organize our Grover's method slightly better, then Grover's complexity here will be square root of this. So it will be fourth root of n. And at the end of this course, so our goal is to understand Shor's algorithm. Well, with Shor's quantum algorithm, we can achieve way more spectacular results. So what we can do is we can do little n squared, which is log base 2 of n squared. And so this is a huge improvement in complexity. So typically, so everything that runs in n steps, so this is called exponential complexity, because big N is 2 to the power n, so it's given by exponential function. So if we have square root of n, this is still the exponential complexity, because this is 2 to the power n over 2, right? And now, so Shor's algorithm gives us a sub-exponential, so it's just a quadratic complexity here, and this is quadratic in the number of bits. So Shor's algorithm is a really amazing application of quantum computing, and this algorithm drives all the efforts that we invest in this area. Now let us discuss Grover's algorithm. So what do we need to do? So our starting state will be this one. So this state incorporates all possible n-bit strings as possible inputs. And each such input comes with the same weight, right? So we have the coefficient in front of each integer k is 1 over square root of 2 to the power n. So this is a rather small number. So what we need to do is we need to apply certain transformation to this initial state. And with the goal of boosting the coefficient at the desired input x equals a. Right? So somehow we need to arrange our unitary transformations in such a way that coefficient at a is increased to a value which is close to 1, and the coefficients at all other inputs is decreased close to 0. Now, how are we going to achieve this? So our tools in Grover's algorithm will be reflections and rotations. So the Grover's algorithm is rather geometric in its nature. Now, let us discuss reflections. Well, suppose our vector space is Rn, and we have some vector u, could be unit vector, in Rn. So what is a reflection with respect to u? So what we do is in Rn we consider a hyperplane that's perpendicular to u. Right, so this is the plane of all vectors that have 0 dot product with u. And then, so the reflection tu has the property that it reflects the vector u itself to its opposite, right? So this means that this vector is reflected to its negative, right? And if so w with u is equal to 0, then so vectors on this hyperplane are not moved by this reflection. And general vectors then, so if we have some vector v, then so what will happen is there will be mirror reflection of v with respect to this hyperplane, and we get so this will be reflection of v in the direction of a vector u. So this is the reflection transformation. So basically, a reflection transformation has two eigenvalues. So the vector u itself has eigenvalue -1, and all vectors that are perpendicular to u will have eigenvalue +1. So we have an invertible transformation, and this transformation is orthogonal, or if we extend this to complex space, this is a unitary transformation, because it sends an orthonormal basis, right? So if we choose an orthonormal basis of the space that consists of a vector u and the basis, orthonormal basis of the perpendicular space, then this orthonormal basis is transformed into an orthonormal basis. All vectors in this hyperplane stay, and u will just go to its opposite. So this means that this is an orthogonal and thus unitary transformation. And so the square of this transformation is clearly identity, right? So if we apply reflection twice, then we get identity transformation. So now we take an n-qubit space, and we want to construct the following reflection, so that I will call R0. So, and the R0 of k is going to be so minus k if k is equal to 0, and k if k is not equal to 0. Well, 0 means 0, 0, 0, 0, right? So this means that the string of all zeros is reflected. So this means that we switch the sign at this term. And all other basis vectors are preserved, right? So here we see that this geometrically this is a reflection because we have one eigenvector with eigenvalue -1, and all other eigenvalues are equal to 1, and so their eigenvectors are perpendicular to each other. Okay, let me make a small correction. I want to call this not R0, but T0. So R will be reserved for rotations, and so this will be a reflection T0. Now let us discuss implementation of this reflection using quantum gates. So the trick is instead of taking an n qubit, we're going to start with n plus 1 qubit. So we're going to add to our input qubit an extra 1 qubit in the state 0. And then to this qubit, we're going to apply OR plus transformation. So the only difference that usually, as we discussed in the previous class, OR is considered as an operator with 2 inputs and 1 output. And here, so this will be an extended OR, which is an OR applied to n bits of this input k. So here, as we said in quantum implementations of classical computations, we need to put together input bits and output bits. So here this k will be considered as input, and the 0 is represent the output, single output bit. Now, what is the result of this multiple OR applied to input bits? So what we are going to get is, so we're going to get the same expression if k is a 0 string. And if k is a non-zero string, then this multiple OR will produce output value of 1. So if k is not equal to 0, right? So this will be a classical computations. So we know how to do this, and so then we get this state. As our next step, we consider the following unitary transformation U of a 1 qubit state. So where 0 is sent to its opposite vector and 1 is sent to itself. So what we see is that here we have standard basis is transformed into an orthogonal basis, right? So the matrix of this transformation is this one, right? Again, so we can see that this is in fact a reflection matrix. So here this is reflection in 0. But because this is a transformation on a single quantum bit, so we treat this as elementary gate. And so now, so we consider a transformation which applies this unitary transformation U on the last bit, right? And so then, so the result of this will be negative k tensor 0 if k is equal to 0, and k tensor with 1 if k is not equal to 0. And as a last step, we're going to undo this OR by applying OR again, now to this state. And so then, so if we apply the same OR now to these inputs, so here we're going to get negative k tensor with 0 if k is equal to 0. And we're going to get k tensor with 0 if k is not equal to 0. And we see that this last auxiliary bit now have decoupled. And so now we can throw it away. And as a result, we get exactly the reflection that we wanted to get. So the 0 bit is reflected, and all other non-zero bits stay where they are. So the next reflection that we need to construct is the reflection TA, which corresponds to this unknown integer a. So TA applied to input k is going to be minus k if k is equal to a, and it will be just the input itself if k is different from a. It turns out that in order to construct this reflection, we don't need to know a, but all we need to know is what is this function f. And basically, the computational scheme is very similar. So we start with input k, and we add an extra bit 0. And then to this, so instead of or plus, we're going to use the function f plus. So f is a computable function. So there is a classical computation that implements the function f plus. And here, so the result will be, so k tensor with 0 if k is equal to a. And it will be k tensor with 1 if k is different from a, right? So because for k equals a, f will produce output 0, and for all other inputs, it will produce value 1. So after this, we apply this unitary reflection on the last bit, and we get minus k tensor with 0 if k is equal to a, and k tensor with 1 if k is different from a. And lastly, we apply f plus again, and so this will give us minus k tensor with 0 if k is equal to a, and it will be k tensor with 0 if k is not equal to a, right? So we know that f plus applied twice gives us identity transformation. So this means that f plus applied to k tensor 0 twice will give us back k tensor 0. And we see that the last quantum bit now is decoupled, and essentially we get this reflection TA. And so this is a key point, that in order to implement this reflection in unknown vector, all we need to know is we need to know this computable function f. And there is one more reflection that we need to construct. So this will be a reflection with respect to our initial state. Let's call it psi, right? So we have this vector that is a superposition of all possible inputs with equal weights. So it's a vector in n-qubit space, which is a unit vector. And so we want to construct a reflection with respect to this vector. So this means that we are looking for a transformation such that, so if we apply it to the vector psi itself, we get minus psi. And if we have some vector phi, which is orthogonal to psi, then t psi applied to phi is going to be phi. Now, so how are we going to construct this transformation? So we claim that we can construct it as a composition of the following things. So let's take nth tensor power of Hadamard composed with T0, right? So this is our reflection that reflected the 0 string. and the composition with the tensor power of the inverse of Hadamard transform. So we claim that the composition of these three things will give us a reflection tip C. So, okay, how do we know this? So we know that if we take nth tensor power of Hadamard and apply it to a zero vector, then the result is the input state Psi, right? So this is this computation here. So this means that if we take the tensor power of the inverse of Hadamard and apply it to Psi, because this is the inverse transformation, the result will be 0. Let's take this right-hand side and apply it to the state Psi. Then when we apply the last factor to Psi, so by this expression, we're going to get the 0. Then if we apply t0 to 0, then we pick up a negative sign. And then when we apply Hadamard to 0, then we get the state Psi, but now with a negative sign. So this means that the state Psi goes to its opposite. Now, suppose we have some vector phi, which is perpendicular to the state Psi. Then we know that Hadamard's transform is unitary. So this means that if we had two mutually orthogonal vectors, then applying a unitary transformation, the images will be still mutually orthogonal. So if Psi gets transformed to 0, so then an orthogonal vector phi will get transformed to something which is orthogonal to 0 string. And what's orthogonal to 0 string? An orthogonal to 0 string is a linear combination of non-zero strings. And then T0 will transform a linear combination of non-zero strings to itself, because all of these will have eigenvalue +1. And then applying the Hadamard again, we're going to get the state phi itself. And so we have that both of these properties hold. And so this composition is the reflection with respect to this composite state Psi. Now, these two reflections, TA and TPC, are the building blocks of the Grover's algorithm. Now we need a little bit of elementary geometry. So suppose we have a plane R2, and we have two reflections. One reflection is with respect to a vector u, and another is a reflection with respect to a vector v. And what we need to do is we need to understand what is the composition of these two reflections. So what is the composition of tv with tu? And so first we apply reflection with respect to u, and then we have reflection with respect to a vector v. And so here we have the following fact from geometry, that a composition of two reflections so TV composed with TU is a rotation in angle 2 alpha, where alpha is the angle between u and v. And so the direction of this rotation is from u to v. So this means, so in this case, so the direction of this rotation will be, well, it will be rotation in 2 alpha and going from u to v. So how can we verify this? So these are linear transformations. So it's enough to check this on two basis vectors. And let's take two basis vectors that are on the lines perpendicular to u and v. So if we take a point A here on the line which is perpendicular to u, then when we take reflection with respect to u, this point is not moved. And when we reflect it with respect to v, then here we get the point A prime. And we see that the point A is in fact rotated by the angle 2 alpha. Now, if I take a point B on the other line, then when we apply TU, it's reflected to a point here. So essentially, we're going by the angle 2 alpha in the wrong direction. And then it's reflected with respect to line TV. So this corresponds to rotating in angle 4 alpha now. And altogether, so this again gives us a rotation, so in angle 2 alpha. So since our transformation is linear, then we conclude that the same will happen to all other points of the plane. And so we conclude that the composition of two reflections is a rotation in angle 2 alpha. Now, what are the steps that we're going to execute? So we start with initial state psi, so this one, and apply repeatedly the composition of two reflections. So we take composition of TA with T psi, right? So essentially, so we are calculating so TA composition with T psi to the power I applied to the state psi, where I goes 0, 1, 2, and so on. Right? So let us analyze what will happen. So a reflection in a unit vector u can also be written as v minus 2 scalar product of u with v times u. Indeed, if we apply this formula to u, then we're going to get u minus 2u, and this will be negative u. And if we apply it to some vector v which is perpendicular to u, then because this will vanish and we're going to get v. So this means that this is an algebraic way of writing a reflection. And here we see that to each vector we add a multiple of a vector u. And so by starting with the state psi and applying these reflections, we are going to add to psi the multiples of psi and a. As a result, we will always stay in a two-dimensional space spanned by a and psi. So this means that this Grover's algorithm actually happens not in a high-dimensional space, but just in a two-dimensional subspace spanned by psi and a. Well, the only thing that a is a hidden direction, so we do not know exactly what it is. But at least this allows us to use this picture. So here we see that everything happens essentially in the space R2, and we can use R2 to analyze this process. Now, we know that this composition is a rotation. Now, let us find the angle of rotation. So the angle of rotation is twice the angle between the vectors a and psi. And these vectors are both unit vectors. So to find the angle between these two vectors, so we know that cosine of angle alpha is equal to the scalar product of a with psi, right? And so what do we have? So here we have the state A, and psi is 1 over square root of 2 to the power n. The sum k goes from 0 to 2 to the n minus 1 times k. Right? So here, if A is, when k is different from A, this scalar product is equal to 0. And so there will be only one term in this sum when k is equal to A, when we get a non-zero scalar product. And so this tells us that the scalar product between these two vectors is 1 over square root of 2 to the power n. Now, this value is very small, right? So this is close to 0. So this tells us that the angle alpha is very close to pi over 2. And so let us write down alpha as pi over 2 minus a small angle beta, right? So this cosine is positive, so this means that alpha is actually less than pi over 2. From trigonometry, we know that sine beta is equal to cos alpha, and which is equal to 1 over square root of 2 to the power n. This means that sine beta is a small value. And then calculus tells us that beta is approximately equal to 1 over square root of 2 to the power n, radians. So we conclude that this composition, so TA composition with T psi, is a rotation in angle to alpha, which is approximately equal to pi minus 2 times 1 over square root of 2 to the power n, right? In the plane, plane spanned by A and psi, so in the direction from psi to A. Right, so now we have the following picture. So we have a vector A, and we have a vector psi. And so the angle between these two vectors is very close to pi over 2, right? So this is the angle alpha between these two vectors. And we start with our initial vector psi, and we apply these rotation operators. So we rotate each time by angle which is close to pi. But rotation in pi may be ignored, because rotation in pi is just multiplying a vector by minus 1. And so all we care about is, so we care about this part. So we have a rotation in pi which we ignore, and a rotation in this small angle. So we choose L such that L times 2 times 1 over square root of 2 to the power n is approximately equal to pi over 2 minus 1 over square root of 2 to the power n. So after L steps, we approach the state, plus minus A, right? Well, it will be plus if L is even, right? So because of this pi. And if L is odd, then we'll get an extra pi, and so it will be minus A, but that doesn't matter. So what we're going to get is, we're going to get a state that has a term with A. So this coefficient at the term with A will be close to plus minus 1. So C is plus minus 1. And this tells us that all other coefficients are going to be very close to 0 because we always preserve the norm, and all vectors have norm 1. And so after measurement, with high probability, we get value A. So what we can see is that by applying these rotations, we are able to boost the coefficient at the desired term A. And then, once we achieve this, then applying the measurement, so if we measure all n bits, then with high probability, we obtain the value of A. So finally, let us say how many steps did we do. So the value of L from here is approximately equal to pi over 4 times square root of 2 to the power n. And so this is pi over 4 times square root of 2 to the power n. And that is pi over 4 times square root of n, right? So remember that n, so this is the number of all possible inputs, is 2 to the power n, where n is the number of bits in our string. So the number of all possible n-bit strings is 2 to the power n. So this means that the complexity of Grover's algorithm is square root of n. So this shows that with a quantum computer we can perform search in a way which is theoretically not possible with classically. So because with brute force it's clear that we can never achieve square root of n. So unless we know special properties of our function, we can only do straightforward search, which will have length on average n over 2. Now, in closing, so let us say that so in this setup we assumed that our function f assumed only one value a, where it assumed 0 value. So what happens if equation f of x is equal to 0 has two solutions? Well, if we know the number of solutions, then this algorithm may be modified, and we can run the same algorithm, but the value of L will be different. So we need a slightly smaller number of steps. And the number of steps that we need depends on the number of solutions of the equation f of x is equal to 0. So if the number of these solutions of f of x is equal to 0 is known, then there is no problem. We can adjust the Grover's algorithm and obtain one of these solutions in this way. So if, on the other hand, the number of solutions is unknown, then we may need to run Grover's algorithm several times trying to guess the number of solutions. So you can see that Grover's algorithm is fairly simple, but tricky. And so this is common with quantum algorithms. So designing quantum algorithms is not easy. And we only know a handful of quantum algorithms at the moment. So basically, so the big question in quantum computing is designing more useful quantum algorithms. And so we see that Grover's algorithm is still exponential in complexity. And so here the Shor's algorithm that we will be discussing in the second half of this course, so that algorithm has complexity of little n squared, which is way better than square root of n. But these are things to come in this course later.